Hi, everybody. It's Professor Mitchell. We are now looking at section 5.3, which is double angle and half angle formulas. Why didn't I say power reducing formulas? Because I am saving those for pre-calc. All right, so you should hear all about those from your pre-calc instructor. We use those a lot in Calc 2. If you don't hear your pre-calc instructor mention power reducing formulas, you should ask them about them. Okay, so we're just going to do a little bit with the double angle formulas and the half angle formulas. All right, so here we go. You can derive these formulas from the sum formulas for sine, cosine, and tangent. I don't really want to get into the details in this video, but the idea basically is that you can get this from, just show you real quick. Oh, let me try using the pen again. If you write, instead of writing the sine of 2 theta, you write the sine of theta plus theta. You just use your sum formula, and that's going to turn into sine theta cosine theta plus cosine theta sine theta. Remember sine, cosine, cosine, sine? All right, and so then those two terms will come out the same, and it will just collapse down to 2 sine theta cosine theta. This is another formula that we use a lot in, really in Calc 2, not so much in Calc 1. You do the same kind of thing with cosine 2 theta, and you get that the cosine of 2 theta is equal to cosine squared theta minus sine squared theta. This one looks a little bit like a Pythagorean identity. If I change this minus to a plus, then that would not equal cosine 2 theta, it would equal 1, right? So that's your double angle formula for cosine. And then I'm going to say the same thing about this that I said about the sum formula for tangent. This one is not as important. I don't remember, I teach Calc 2 pretty frequently. I don't remember using this formula ever in Calc 2. Okay. So but these two we do use quite a bit. Okay. All right, so here's an example of something that we do with the double angle formula. So we're given that the sine of theta is 4/5 and theta is in quadrant 2. I remember doing a problem just like this in section 5.2. That is enough information to find the exact value of sine 2 theta. Okay. So the first thing I'm going to do is remember the formula. Sine 2 theta is 2 sine theta cosine theta. So the good news is that I know sine theta is 4/5. The bad news is that I don't know the cosine of theta. Okay. But I think you know how to find it, right? Because we just had to do that in section 5.2. You're going to use either your Pythagorean identity or you're going to use your definition of trig function at any angle. And I think they like to do it the second way that I said. So there's a picture of angle theta. It's sitting over here in quadrant 2. Y is 4, R is 5. So we're going to solve for x using the Pythagorean theorem. It turns out that x squared is 9, which just like in the last problem we did that was like this means x is -3 because this angle is in quadrant 2, right? X is pretty clearly a negative value because it's sitting over here on the left side. So now I have everything I need to finish this off. Cosine of theta is -3/5. That means the sine of 2 theta is going to be 2 times 4/5 times -3/5. And when you multiply all of those things together, we'll sneak a 1 under here if you find that helpful. That is going to come out to -24/25. Okay, so the next example, I guess they're considering it the same example. So again, given that the sine of theta is 4/5 and theta is in quadrant 2, now we can find the exact value of cosine 2 theta. Okay. So, starting with the double angle formula for cosine, which is this. We already, in the last problem, are they going to do this all over again? No, they're not. Okay. So they're using the values that we found in the last problem. We're given that the sine of theta is 4/5. And in the last problem, we had to find that the cosine of theta was -3/5. So now we're going to square the -3/5. We're going to square the 4/5. That's going to give me 9/25 minus 16/25, which comes out to -7/25. The cosine of 2 theta is -7/25. Okay, so now we're going to, given the same, setting, sine theta is 4/5, theta is in quadrant 2, find the exact value of tangent 2 theta. There are two good ways to do this. One of them is to use the double angle formula for tangent. Now, the only thing is, we have not figured out the tangent of theta yet. We haven't needed it. So before so I'm going to have to do that first, right? So remember the tangent of theta is y over x, and we have already, well, we were given that y is 4, and we figured out that x is -3. So tangent theta is -4/3. So when I plug that into this formula, I get 2 times -4/3 over 1 minus the square of -4/3, which comes out to, whoops, okay, just 1 second. All right, so now we just have to simplify that down. So 2 times -4/3 is -8/3. The square of -4/3 is 16/9. 1 minus 16/9 is -7/9. So the tangent of 2 theta is going to be whatever -8/3 divided by -7/9 is. How much work did they show for that? Oh, good. Dividing by -7/9 is the same thing as multiplying by -9/7. And when you multiply -8/3 times 9/7, let's see, it would help if I hit the draw button. 3 into 9 goes 3. These negative signs disappear. You're left with 24/7. Okay, so the tangent of 2 theta is 24/7. Now there is an easier way to do that. Since the previous 2 examples were finding the sine of 2 theta and the cosine of 2 theta, why wouldn't you just go ahead and use those and use your quotient identity? So let me think. The sine of 2 theta was -24/25, I think. Yeah. And the cosine of 2 theta was -7/25. So when you divide those 2 fractions, I was doing well with the pen, you get 24/7. And that is a much easier way to do that problem. But at least I got the same answer doing it both ways. All right. There are 3 different forms for the double angle formula for cosine. So up top here is the one that I've already shown you. And it turns out, and this is a very easy 5.1 problem. It turns out that that's the same thing as this, and it's the same thing as this. And let me explain why, and then explain, what good this does you. If you take one of your Pythagorean identities, so I'm going to start with this thing right here. So you know, for example, that the sine squared of theta is equal to 1 minus the cosine squared of theta. That is a Pythagorean identity. So when you simplify that, I think you get the thing that's on the second line, right? You get cosine squared theta. You distribute this minus sign, you get -1 plus cosine squared theta. You combine your like terms. Voila, you get what's on the second line. And what I really like about these alternative forms of the double angle formula is this one only requires you to know the cosine of theta. It does not require you to know sine theta. And this one here only requires me to know sine theta, does not require me to know cosine theta. So if they had only told me about this a few slides back, then I could have done the second example, finding the cosine of 2 theta, given that sine theta is 4/5. I could have done that using just the bottom formula, right? So taking form number 3 here, remember the sine of theta was 4/5. So this would turn into 1 minus 2 times 4/5 squared. The square of 4/5 is 16/25. 2 times 16/25 is 32/25. And then when you get your common denominator, I have figured out, I think, what's going on with the pen. When I get further down the screen, I write sloppier because of the way my hand is positioned here. I need to move the tablet back. All right. You get your common denominator. 25 minus 32 is -7. So that's an easier way to do that problem because, again, I don't need to know that the cosine of theta is -3/5. All right. Next, we have the half-angle formulas. Now, the half-angle formulas are derived from the power-reducing formulas, which I skipped. Again, I think power-reducing formulas are a great topic for pre-calc. All right, so maybe when you get to pre-calc, you'll see an explanation of how these relate to the power-reducing formulas. Some books don't even use the term power-reducing formula. They just call them half-angle formulas because they really are just a different form of these things. Okay, so forget about, oh, okay. When I first looked at this, I was wondering, are they going to say this formula in words and think that that's helpful? But that's not what they're doing. So for example, it's saying the sine of alpha over 2 is equal to either the positive or negative square root of 1 minus the cosine alpha over 2. And what they're explaining down here is the way that you figure out whether the answer is ultimately plus or minus is by figuring out what quadrant is the angle alpha over 2 in, all right? And you will definitely see an example of that here in a minute. Notice that the formulas for sine and cosine are very, very similar. The only difference is sine gets a minus, cosine gets a plus. And I'm going to say the same thing I've been saying about tangent. I don't find this one as important. If I need to do something with the tangent, I'm probably just going to think of it as the sine over the cosine. Okay. All right, so coming up next here, I think we have an example of using half-angle formula. Okay, so here's a great example of using a half-angle formula. We're going to use the fact that the cosine of 210 degrees is -√3 over 2. And that's something they really didn't have to tell you, right? You could have figured that out. But they're being nice, and they're telling me that the cosine of 210 degrees is -√3 over 2. And I'm going to use that to find the exact value of the cosine of 105 degrees. Okay. Notice that 105 degrees is half of 210 degrees. That's why we're going to use a half-angle formula. So, okay, so that's what I just said about 105 degrees is half of 210. So playing the role of alpha in this problem is 210 degrees. So here is my half-angle formula for cosine. I'm going to replace alpha with 210 degrees. And that's going to give me over here 1 plus the cosine of 210 degrees over 2. Notice that they have already put they've already chosen to put a negative sign here. My plus or minus turned into a negative. And why is that? Because think about which quadrant 105 degrees is in. 105 degrees is in quadrant 2, right? And in quadrant 2, the cosine is negative. Okay. All right, so here's the value that they gave me. The cosine of 210 degrees is negative root 3 over 2. So now on the next slide, what's going to happen is we're just going to simplify this mess. Okay, so finishing up this problem, we have already figured out that the cosine of 105 degrees is equal to this ugly thing. So now we're going to simplify that ugly thing, and I noticed when I was putting this together, okay, so I'm trying to remember if we ever went over simplifying complex fractions in this class, and I think that might have been something that I skipped in section P6, bad instructor. So the way I'm going to simplify this is I am going to multiply the top and the bottom of this big fraction by 2, right? So that 2 is going to get distributed here and here. And then on the bottom, that's easy. That's just going to be 2 times 2. It's the same thing you see here. I just thought I could write it a little more clearly. Okay. So then, after you distribute that 2, 1 times 2 is 2. Negative root 3 over 2 times 2, the 2's cancel and just leave me root 3. And then on the bottom, you have 2 times 2 is 4. And then we can use the quotient rule for radicals. You have this radical over the whole entire thing. So the bottom becomes a 2 because it's just the square root of 4, right? Okay, so final answer. The cosine of 105 degrees is negative square root of 2 minus the square root of 3 all over 2. Now, there's something interesting with problems like this. Another way to find the exact value of cosine 105 degrees is to use either a sum or difference formula. So here's a fun little exercise. Do this problem again, find the exact value of cosine 105 degrees by thinking of 105 degrees as 60 plus, see, I told you it was sensitive. The cosine of 60 plus 45 degrees. And then use your addition formula for cosine. Cosine, cosine minus sine, sine. You get the same answer, but it looks completely different. And so then what you can do is just use your calculator to check that they are in fact the same value, because they definitely don't look the same. All right, we will end this video by just pointing out that there are half-angle formulas for tangent. I think I actually showed you one on a previous slide. These ones just look a little prettier. Notice they don't have the radical in them and they don't have the plus or minus. All right. So I would say that one of these formulas is probably preferable if you're trying to find the tangent of alpha over 2.